Okay, today Ziqian will tell us about some introduction to Instanton coming from the Young's Mu action.
Yes. So I will say about what is Instanton, and so let us say, so why I chose to do Instanton is because for my topic, and then I read about the paper, then I found out that the polynomial is categorized by the Higa floor theory. And then in this theory, they define their differential by counting this instanton. And why they choose to have this theory, because this theory turned out that they can solve the question explicitly. So for me, my interest is what is the instanton. Then I start to study about the instanton, what happened to it. So in instanton is actually comes out from physics. So it is a solution of equation of motion. So I have to say what is equation of motions. The equation of motion describe about a function that is depend on the position and the time. And then if we write the position into a time, then it is actually a second order differential ODE. Then the definition of instanton is the non-singular solution of classical equation of motion in Euclidean space, and their action is finite. So let me explain the terms. The non-singular is actually the analytic solution, because instanton, we write them as the function of time, write the position as function of time. So it is analytic to the z, to the t. And then the equation of motion is the equation just now I mentioned. And then action is finite. The action in physics is actually about that we integrate the instanton, and over the time, the integration should be finite. So let us go to some manifold definition before we look at the example of instanton. So the definition of vector bundle is we are given two manifold and a map from E to M such that pi is locally trivial at rank R. So what is locally trivial at rank R? That is for every point in M, the pre-image of P has a structure of vector space. So it satisfies the 10 axiom for the vector space. And for all point of M, there is a neighborhood U of P, and there exists a diffeomorphism from pi inverse U to U times R to the power of R. And such that for every point in M, the pi inverse of Q is isomorphic to the 1 point Q multiplied by R to the powers of R in the sense of vector space isomorphism. And in this case, we call this phi is the local trivialization. And then if we abuse the notation and call the E is actually a vector bundle over M. And next, A Lie group is actually a group, but the group G is also a smooth manifold, and also the multiplication and inversion inside the group is smooth in the sense of manifold. So equivalently, the map that maps 2 points in G to X inverse multiplied by Y is a smooth map in manifold. Next, I want to introduce the principal G bundle. So if M is a manifold and G is a Lie group, so principal fiber bundle P over M with the Lie group G should satisfy the 3 points. First, G should act freely on P at the right side. So there are some equivalence meaning. So I choose that this for every, we choose one U from the P and A from the G, then U multiplies by A should in the P, or we say A multiplies U at the right side.
What is
And
going
then
on? What is X in G here? Where is A is in G, X in G?
Here I write UA equals to RAU. So I need to explain what is this RAU. So I use another notation to say that
You use the same
it's
notation,
P,
right?
P is actually P. So E is a right action between A and G and X in P actually. And then A act on X by multiply at right side.
So that's a typo, is it?
That's a typo, yes, that's a typo. X in P.
You already defined RA, so you don't need it.
Okay. And then M is equal to P quotient to G by the equivalence relation induced by G. And the third point, P should be locally trivial. That means for every point there is a U such that pi inverse U is isomorphic with U times G, which is just now I mentioned that the local trivialization exists.
Wait, Zixian. So why? Yeah, right. So Aras point out why you write the note again, because you already write down the definition.
Yes, just a reminder for me.
I
But
mean,
turns
it's the
out
same.
I don't need.
It's the same thing, right?
Yes.
Okay.
Okay. And then after the principal G bundle, we come to the principal connection. So principal connection is one form, a map that maps one form on P to the value in Lie algebra. Also, we can say the principal connection is a projection from the tangent space of the P to the vertical space of P. Vertical space of P is actually given by the kernel of the map induced by pi. And this one is isomorphic to the P times G, and where the G is the value of Lie algebra. Then next, if we have a principal G bundle, a vector space, and they both have the structure of the G, and then we can have a associated bundle. That is, we define the multiplication in P and V by P times P cross V, but we identify the P times G at the first component and V at the second component is same as P at the first component and G times V at the second component, because we already defined how G act on P and V both. And then the next one is the section of the vector bundle. So a section on the vector bundle is mapping every point on the E to one of the mapping every point of M to the pre-image of it. Map P to the one of the pre-image of P. So in other words, pi composite with this S is identity on the M. And we denote that all the smooth section of a vector bundle is gamma E. And next one, a connection on a vector bundle E is a linear map from the smooth section to the one form, and it should satisfy the Leibniz rule. So we have so many definitions, so I decided to put one example for this. So we have a matrix, then we can actually define a connection by taking a derivative on, we say this delta act on S by partial X on S plus the matrix multiplied by the section. So for example, we choose the section to be X, Y go to 5X, 4Y, and let F to be the function fxy equal to 3x squared. And then by computation, the delta act on fs, we get the first thing we see. And we also compute that the f delta s plus df tensor product with s. And then at the last two lines, we see that these two are actually same. This is the way to show why this works.
Can you comment like why it works for OF? Do you need to show for OF, right? Do you need to show for all F there's a infinitely differentiable?
Sorry, the network is not good.
Hello, can you hear? Hello.
Because they are all polynomial, so they are just infinitely differentiable.
I mean there are others infinitely differentiable function, right?
Yes.
So a connection have to satisfy the Leibniz rule for all infinitely differentiable function.
Yes, a connection should satisfy for all, but
so
I can.
Yeah. So this is
if I choose
yeah.
a function that is easier to show.
Yeah, I know. Like, can you like straight away like comment why is it true for all?
Why is it true for all?
Yeah.
For
all F.
Because like for the definition, and then we check if we have fs, the first component, the
What do you
adding
want
has
to
two
prove?
parts.
What do you want to prove? You want to prove that this is a connection, or what is the goal?
I want to show how this act as a connection on a chosen function, and we choose the function as 3x squared and choose a section just to see what it happened.
Okay, so you don't want to prove that it's a connection, right? You already accepted it's a connection. You just
Yes.
want to apply it for F and S, a particular F and S. That's it?
Yes, but I still can explain what happened to it because delta Fs, we can see this. The first term we are partial to the Fs, where Fs is actually direct product. So we have this partial add on it, then it should obey the Leibniz rule. And the second part is matrix multiplication, so it just distribute over it. So the Leibniz rule is keeping on the first term, the partial part.
Yeah, I mean, wait, let me see. Yeah, I think it's better to just do it for general F instead of compute some specific F.
First, prove that it's a connection. Okay, then you can
Yeah.
calculate if you want, but you haven't shown that this is a connection yet, right?
Yeah.
Is it a
Yeah.
connection?
Yes. Instead, in the reference, there is one theorem saying that the connection can be given any matrix, we can have a connection by doing the delta defined to be gradient taken on x, s plus the matrix multiplied by the s.
So we don't need the matrix to be in GL2 or what? Do we need it to be any condition on the matrix?
I think it is invertible is of course work.
Have you checked that this is a connection or not?
No, I will not check it. I just give a visualization what happened to it.
I think if you provide the theorem is better than doing this calculation.
Okay.
Yeah.
We will see the result at the behind part, not the theorem. Let us look at
because the example doesn't shed much light. If you have stronger statement, is better to appreciate.
Okay.
Yeah.
So we goes to the next part. So
Maybe you have to put Laplacian there if you want the connection. With ddx, I don't think you get a connection.
Yes. So for the next part, if a vector space has an inner product, we can try to have a inner product on multiple U and V on the exterior product. So by defining U1 wedge until UK and V1 wedge until VK for the inner product on the wedge to be the determinant of we picking any 2K and J to do the inner product. This inner product can extend to the whole lambda KV by the binarity of the inner product.
It's W1, W2 here, 1 and 2 is index, right?
Yes, it is index. Yes.
So why you don't write as an index, you write it like this?
It go wrong
Is it typo?
It's a typo. It's hypo. It's typo, yes. So in the corrector, we chose W1 and W2 and define the
and V star is the
inner
dual
product
of V, right? V star is the dual of V.
Yes.
Have you used ChatGPT to produce this?
No?
But why too many people like this?
No, I looking at the textbook and type and
I know,
Yes.
but you see, okay, it's not one mistake. You have W1, the index is written there. W2, again repeated. Then V star, star should be on top. Then lambda K, V star, again, a star should be on top. So you
What?
have how
Oh,
many
yeah.
mistakes in one line?
Do
To
you
Sorry.
me,
just
it looks
like
like ChatGPT, the mistake similar to ChatGPT.
No. No.
Okay,
Because I copy it from the behind, and
okay.
I
do you
didn't.
do you just like when you type W1, W2, you just copy the next time?
Yes. Yes. So we see this. We see this hostile operator is we taking alpha from the lambda k, and beta is also is from the lambda n minus k. Then we say that the wedge between two these two are given by a unique alternating tensor in the lambda n minus k. So this star A and B is same dimension, then they can do the, the inner product I just defined, and then multiply by E1 wedge E2 until En. There one more wedge
What
is
what
hypo.
what is here again? It's a typo, or I can see a
Hypo on
wedge
the first wedge.
here. Okay.
Hypo is inner product multiplies by the E1 wedge until En. And the theorem says that this kind of the unique alternating tensor is independent to the basis E1 until En as long as the orientation don't change. So here I give a proof to it by using other some theorem for it.
You already passed the time. I don't think you need to give a proof.
Okay. And we have already defined the operator on the k tensor to the n minus k tensor. So actually, if we change the v to the v star, it is also work, and it give a map from the k form to the n minus k form. And we have defined already what is a connection and principal connection. Then we can extend the connection to a family of map. And this if it satisfies the Leibniz rule, and we get a sequence. And we say the D delta composite with the delta is the curvature form, which is mapping the A0 to A2. Here, A0, A1 is the AI is the I form. I say like this. So A0 is the set of 0 form. A1 is the set of 1 form. And then the curvature matrix can be represented by a matrix. And actually, the connection I mentioned before can also represented by a matrix in a similar way. And then we have the structure equation. It says that the curvature matrix can link with the connection matrix by this formula, which is the d omega plus omega wedge omega. And from this structure equation, it reduced to the Qian key identity, which is the d omega equals to omega. I mean the connection map is the curvature map is the connection minus the connection wedge with the curvature. And then we can see an example for the instanton, which is the easiest example. So we give a instanton, for example, which is the Yang-Mills equation. So the equation is actually the dA hot star with the FA is equals to 0, and the curvature is the solution, is the desired instanton. And the trivial example of the solution is if we can find a self-dual connection or anti-self-dual connection, which if we do hot star, we get positive FA or negative FA, then of course this FA should solve the Yang-Mills equation. So is all. And some of my reference are come from these books.
Okay, Arash, do you want to ask
Okay,
some
thank you.
questions? Yeah.
I think it's okay, but you have to be careful about this typos, and maybe you should understand better what you are saying, huh?
Okay.
Okay. So I think that's it. I don't have particular question.
Okay. So thank you, Arash. And we'll end the talk today.
Bye bye.
Thank you.
Bye
Thank
bye.
you, sir.